Okay, this is 2.3. So, as I was mentioning, we're exploring instantaneous rates of change using graphs. So it's just kind of the same idea of yesterday. The only difference is now we focus a little more on the actual graph. Anybody ready to read, explore the math? Yeah, thanks, Elijah.
In the previous lesson, you used numerical and algebraic techniques to estimate instantaneous rates of change. Graphically, you have seen that the average rate of change is equivalent to the slope of the secant line that passes through the 2 points on the graph of a function.
Okay. How can you use the slopes of a secant line to estimate the instantaneous rates of change? So who could answer this already, just based on yesterday's lesson? I hope most of you should know this. How can you use the slopes of a secant line to estimate the rate of change? Nobody? Please? Yeah, Alex, thank you.
If you bring your the points on the slope closer to the point, then you have a better estimate of the tangent line.
Perfect. So if here's your point of interest, we know what a tangent line looks like. It looks like this. Here's our secant line, 2 points. So there's your secant, and here's your tangent. So as you reduce the difference between the point of interest and the 2 points on the secant line, that slope becomes more and more approximated to the tangent line. That makes sense? We talked about that in depth yesterday, right? Like I just kept going over that. Okay, so all we're showing that today is that fact. So it says enter the function f at x equals x squared into the equation editor of your graphing calculator. Graph it and draw a sketch of the graph. So we know what that graph looks like, right? We should be really familiar with that since grade 10. And we have this step pattern happening of 1, 1. So this point is 1, 1. Then we go 1 over 3 up, so this is 1, 4. And we go 1 over 5 up, so this is 2, 4, 3, 9. Okay. Okay, that's just y equals x squared. Been doing that graph forever. On your sketch, draw a secant line that passes through the points 1 and 3. X values 1 and 3. So here's our secant line passing through those 2 points. Any questions there? Okay. Calculate the slope of the secant line. Copy the table and record the slope. So remember, slope we know is y2 minus y1 over x2 minus x1. For the first example, our point is 1, f at 1. So we have f at 3 minus f at 1 over 3 minus 1. F at 3 is 3 squared minus 1 squared over 2. 9 minus 1 is 8 over 2. Our slope is 4. Any questions there? So this slope of the secant line here becomes 4. Okay, we use the exact same process, but now we're using x value 2, y at f at 2, and we get these values of our secant. 3, 2.5, 2.1, 2.01. Do I need to do this 4 times to show everybody, or are you guys all good with this? Any questions? Okay, so yeah, you're just plugging in this x value and this x value and solving for y and then subtracting the y's over the difference in the x's. Okay, so we can see what's happening then. If here's our graph, and try and blow it up as much as I can. So we go 1, 3, 1, 2, and we're going smaller. So we're going from this secant line to this secant line to this secant line. Okay, so our slope is going down from 4, 3, 2.5 to 2, and we're approximating a slope of 2. Okay, these values, the difference in x values are going from 3 to 1.5, 1.1, 1.01. So our last slope is like really close, right? Any questions? So next it says D, create a formula for calculating the slope of any secant line that passes through 1, f at 1, and a general point x at f at x. Who can tell me how I would write that formula out? Jesse, here's a shot. So what is this? What is the equation for a slope formula? M equals
delta y over delta x.
Okay, which is
y2 minus y1
okay.
over x2 minus x1.
Okay, good. So now we want to do it for this point and this point. This is going to be x2 y2, right? And this will be x1 y1, right? So go ahead, help me out. And we're going to put in the function, right? The function is up here. So what is y2? Right here, I said y2. What's y2?
F at x.
Okay, which is what in this function?
X squared.
Good. Okay, good. Thank you. X squared, not a trick question, minus y1,
Y1.
which
So
is
1.
1 squared, right? Good. Over?
X
Good.
minus 1.
Good. Anyone confused by what he did? Simple, right? These are the 2 points they gave us. We're using them. We're plugging them into the function up here. I showed you how to do that earlier. Whatever's in brackets goes in for x. It's really easy on this function because this function is so simple. But as it gets more complicated, you have to remember that rule. All right, so we have x squared minus 1 squared over x minus 1. Who knows how to factor this numerator? Can't do much with the denominator, but the numerator you guys should recognize. David. You recognize what's happening here? Did you see what I'm talking about? This, David, what do you notice? This is called a difference of? Can someone help him out? Yeah, Joseph?
X minus 1 and x plus 1.
Good. So he factored it, right? Because it's a difference of squares. You got to recognize that, guys, when you have squares written out. And I wrote it like that on purpose. I didn't put minus 1 because that would have been maybe confusing. I put minus 1 squared to show you guys difference of squares, okay? These are just the type of things you have to start recognizing. Now what can I do? Joseph over here. Sorry? I'm talking to Joseph over here. You can't see?
It should be x plus 1 times x minus 1, right?
Yeah, so what can I do?
So you're gonna have to divide, and on the bottom is that x minus 1?
Yes.
So then you're gonna cancel the x minus 1.
Thank you. Yeah, that's all I'm looking to do. So there's our slope. Okay, so now if we were to use this slope, our x value we're just adding 1 to. So notice this, the x value is 3, our slope is 4. The x value is 2, the slope is 3. The x value is 1.5, slope is 2.5. See that? You see how much faster that was? Instead of doing this every time, we created a nice little neat formula using algebra and boom. Next it says enter into your this formula into your equation editor. So you should have these apps on your phones. You can try this at home. You can actually put, as I mentioned, this exact graphing calculator. So it will have this button, TBL set, table set, on your phone. So not a bad idea to do. So I'm going to put here It's the name of the calculator. It's like the TI-875 or whatever. It's in your textbook at the back in the appendix, okay? Just search up that name and you'll see it. So phone app. Do at home or in the class later. Okay, so it's confirmed. It just wants us to confirm these slopes. We know they're right. Okay, next it says, on your sketch, draw another secant line that passes through the points 1 and 2. Calculate its slope by entering x equals 2 in the table on your graphing calculator and compare this to the slope you entered. So this is exactly what we've already done. I was just showing you, you actually get the same slope by just using the formula. Draw and calculate the other secant lines. We've done all that. You can do this by using the points in part C. So we've done that. Examine your sketch and your table of secant slopes. So let's show you this. Okay, this is what it should look like. Okay, so here's what I was trying to draw, just a lot better. There's the point of interest where x is 1. Okay, here's x is 3, so there's our first secant line. There's our next secant line at x equals 2. And see how as we gradually take the secant lines between points that are closer together, we get closer and closer to a tangent line. Okay? So as the distance of the two secant points okay? As the points become closer and closer together, the line becomes more and more like the tangent line. Any questions there? Okay, another way of saying that is instead of as the distance of the two points come closer and closer together, you could say all this by saying as h gets smaller. Remember what h is from yesterday. It's a small x value, okay? And it's typically added to the a value of x, or the x coordinate of the point of interest. Okay. Any questions? Okay, examine your sketch. Describe what happens to each secant line in your sketch and compare this with the values of the slopes in your table. So I think we've done that, right? So we're seeing that the slopes get smaller and smaller, or sorry, less and less. We see that it goes 4, 3, 2, and 2.01. Okay? Estimate the slope of the tangent to the curve f at x equals x squared. Who wants to estimate this? How about Gennaro? So, okay, we're going to estimate the tangent line, the slope of the tangent line to the curve at this point. So, what do you think, Gennaro? Okay, Gennaro, look up here for a sec. Here's our secant slopes, right? 4, 3, 2.5, 2.1, 2.01. What do you think the slope of the tangent line is going to be when they keep getting smaller and smaller and smaller? Now it's like two dots very, very close together. What do you think the slope of the tangent will be? Right, 2. Okay? So slope is going to be 2. Okay? And I think I explained yesterday what a tangent line is, but here it is again. Okay? It's a line that touches the graph at only one point P. within small interval of relation. It could, but does not have to cross the graph at another point outside this interval. So it could cross through again somewhere. But I'm not even sure why they mentioned that. I don't know why that's even relevant. Because if I was drawing a tangent line, I'm only going to draw it like this anyways. I don't know why this has any relevance at all. So this whole part, it could, outside the interval, all of this, I don't know if you even need that. It's just it's a line that touches the graph at one point.
So
Yep.
I think what you're trying to say is like the point of interest. Like it only tells you the point of interest once.
Yeah, it tells you the slope of the curve at the point of interest.
Yeah, so like even though the line can touch like another point, it's like if it's not the point of interest.
Yeah, I just don't think it's that important why it's mentioning that. You like they're not drawing the line over here and saying, "Oh, it could go on forever down here." It doesn't matter. Like this is the tangent line, right? That's what you should focus on. Yeah.
But if it only says 1 point, how could it cross another part of the graph?
That's point of interest.
So are they wrong? 'Cause like,
Point is not the point
No,
of
that's
interest.
probably why it's putting that in for silly questions like the one you just asked, Luigi.
Yeah.
That's the only reason they put it in. This is just for you, Luigi. It could, but does not have to. Okay? For that one question that you asked,
so
that's why it's there.
Because at the beginning it says
That's why it's
only
there.
1 point.
No,
Right, so they don't contradict themselves, they put that in, Luigi, for you. Okay? Just for you. Alright?
Like then you were gonna take.
See, some student probably asked that question, but it only touches at one point, but then it touched again over here. So that's why they had to put all that in. Alright?
Thanks a lot.
Okay. Estimate the slope of the tangent line of the curve x squared. It's m equals 2, okay? Gennaro told us that. Repeats b and k using the 2 points in the table of values. So what they're doing now, guys, is look, they're coming from the other side. They're coming from -1, 0, 0.5, 0.9, 0.99. So now, we look back at this graph. Now they're coming from, sorry, where's that other graph? They're coming from this side. So they're starting at -1, and their tangent looks like this now. Okay? So now what they're doing is like this. Alright? So, if we do that same calculation here, y2 minus y1 over x2 minus x1, which is y at -1, so -1 squared minus 1 squared over -1 minus 1, we get 0.
Sir.
Okay, so the first one is 0. We do that calculation again, we get 1, 1.5.
Would the same equation not work? That we made last time? Or what it was?
Sorry guys, I can't have talking over here. If you have a question, please put your hand up. Luke?
Would the same equation that we made the m or the x plus 1 not work for the other side of the line as well?
Which equation?
We had taken the
Algebraic.
we algebraically made a slope equation where it was just x plus 1.
Yeah, no, it would definitely work. Sure it would work.
Oh.
Because it's the same function. Yeah, so you're right. Why not just use it, right?
Yeah.
1 plus, what was it? X plus 1?
X plus 1.
So here's our x, plus 1 is 0, 0 plus 1 is 1.5, plus 1 is 1.5. Okay? Yeah, you're right. Verify your estimates by drawing the tangent line to the graph using your graphing calculator. Looks good to me, right? These 2 points. If we look here now, our slope goes from 0 and it goes again. Now it's increasing up to 2. Repeats b and l with 2 other functions of your choice. Use 2 different types of functions such as an exponential function, a sinusoidal function, or a different quadratic function. You can do this for fun at home. Okay? Not doing that. Alright. What happens to the slope of the secant lines as the points move closer to the fixed point? We've done this like 10 times now. Joseph talking in the back to Alan. Oh. Oh. See how long it's taking you to answer a very simple question, Joseph?
Doesn't it get less steep?
less steep. No. In the case of this example, it gets more steep.
It gets closer to the tangent line.
Yes. And that's what we've been saying now for like 2 classes, right? So just stay focused, okay? Because I'm not trying to... Well, I was trying to show you up, but I just want you to stay focused, okay? I just want you to stay focused, because it's easy, but if you're talking to Alan in the back there, you're going to not get it, okay? How do the slopes of the secant lines relate to the slope of the tangent line when x equals 1? Okay, this is all we've talked about the whole lesson, right? They become the tangent line as the difference between the 2 points becomes less and less. How is estimating the slope of a tangent line like estimating the instantaneous rate of change? It is the,
Same.
as they say in Thailand, same, but different.
Same squared.
It's the same thing, right? We're just using it, we're just doing it by using a graph, okay? An instantaneous rate of change, we were using it by algebra, okay?
Hey.
In summary, beautiful graph here, guys. If you were asleep for part of this lesson, this is probably the one and only page you need. Look at these nice, beautiful colors. It would take me 45 minutes to try and replicate this on the board. Okay, so tons of time saved here. As Q approaches P from the left, the slope of QP increases. So we're going like this, boom, 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 boom. As Q approaches P from the right, the slope of QP decreases, boom, 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 boom. Okay, there's our colors. And red is our beautiful tangent line, and yellow, green, and blue are our secant lines as they become progressively closer. Any questions?
So sir,
Yeah.
if you approach from the following points,
Mhm.
that means that the slope of the line is steeper.
If you approach from the following point would be the right side, so it's actually getting less.
Okay, that's
Yeah.
and it would be the opposite for if it's the previous.
Yeah, it's not so important that you understand that. Just conceptually, you guys should understand this, right? Like what's happening, right? Don't worry so much about the wording. It's important you understand. Okay, any questions? 2.3?